Okay, here's what we're going to do. We're going to call this one M1 and this one M2. And then we'll get to the end of the problem. We'll see what we have to do with it. I'm going to start off by reminding you that they all begin the same way. I'm going to do M2G downwards, tension upwards. I'm going to make a prediction. This is the way it's going to go. And moreover, I'm going to assume the net force equal to MA until proven otherwise. Now this one tells me to set it up so the net force equals 0, but I have a plan, so I'm going to do it this way. Free body diagram over here, a little more complicated. M1G normal tension. Now just a couple of things to remind you about. That's the worst dotted line ever. It's not gray, but it'll do. Now we're going to make this the positive direction, and this negative and this positive, this negative. So based on that, this is theta from there. So I will have a mg cosine theta that way, and an mg sine theta that way. For notes on why those are cosine and sine, check your notes. This is a right angle. Mg sine theta is all in the x direction. Mg cosine theta is all in the y direction. So, if I was going to take a look at the net force in the x direction for the one on the incline, I'm going to have T minus m1g sine theta equals m1a. So T minus m1g sine theta equals m1a. That's it. That's all I really need. That's what I got over there. Here I'm going to have m2g minus tension equals m2a. So if I want the acceleration of the system, I have to eliminate tension. We've kind of talked about this a lot. I could solve one of these for tension and eliminate the other one. I could solve them both for tension and set them equal to each other. Or, my favorite, I'm going to write this as negative m1g sine theta plus tension equals m1a. Just flip the order, so that I can add those things together. First thing I'll point out is I get a positive t and a negative t, so those get wiped away. I'll have m2g minus m1g sine theta equals, so I've taken care of this side, put it there. I'm going to add together that side and get m1a plus m2a. Alright, well, that's really about it. I'm going to solve for a. So I get m2g minus m1g sine theta equals, I'm going to factor out the a, get m1 plus m2 all times a. Please notice this. That's the inertia of the entire system, right? Mass is inertia of m2, inertia of m1, all added together. Also, I got this wonderful negative sign here, which tells me that it goes down the ramp whenever this one is bigger than this one. Because if this is bigger, this whole thing will be negative, so the acceleration will be negative. It'll go down the ramp that way. If this one is bigger than this one, the whole thing will be positive, and it'll go up the ramp this way. But they're interested in what happens when the acceleration is 0. So then I get m2g minus m1g sine theta equals 0. Cancel the g, and let's solve for theta. I'll get m2 equals m1 sine theta. So let's take this all the way up top, sine theta equals m2 minus, sorry, m2 divided by m1. Well, that's really it. This can only be between 0 and 1. That can only be between 0 and 1. That means that the only way I can even get balance is if m1 is greater than m2. Now, in the problem, they told me that the one hung off the table is twice the mass as the one that's on the table. So that means 2m over m equals sine theta. There is no angle. Sine theta can't be equal to 2, so there's no way for the system to be at rest, no way for the system not to accelerate. Yikes. What a mess. Okay, this problem a lot easier than it sounds. This is m, this is m, so this is mg, this is t, this is t, this is mg. Although a lot of people think the tension is like twice the weight, the truth is net force equals 0, so tension minus mg equals 0. Tension equals mg. That's all there is. That's the tension in the cord. I'd like for it to be more complicated than that, but no, not really. So let's go on to the next one. We've got 2 boxes. That box. And this box. And they are attached by a thin cord, like so. Okay, so there it is. Initially, somebody's holding this box right here, and we're asked what's tension in the string, and then we're going to release the boxes and ask what's tension in the string. So, if this were M1, this were M2, I want to know the tension in the string when I'm holding it. Well, this box is what's creating that tension in the string. So net force would equal 0, so T minus M2G equals 0, so T would equal the weight of the second box. So I think it tells me that this is actually twice the mass of this one, so it would be twice the mass, 2 mg. So if I let it go and they both start falling, they're going to accelerate downwards at g. So what's the tension in the cable now? Well, to find the tension in the cable now, recognize that it's not equal to 0. It's now equal to ma, where this is the acceleration of gravity. If that's true, then when I solve for the tension, I get T minus M2G equals M2G. But G is downwards, and I've made this negative, so my acceleration is negative. So that's going to be T minus M2G equals negative M2G, which means T equals 0. When you drop it, there's no tension in the cable. There's nothing to provide tension in the cable. The top box is moving downwards at the same speed the bottom box is. So that's number 6.